The name of this video is Feynman Capacitance. Eventually, later on in this course, we are going to encounter the Maxwell's inductance. So we will consider two famous physicists. One has developed an interesting method to find a capacitance, the other one, how to find an inductance. So this is our usual back-to-back between E and B in this course. Okay, so in one of the previous videos, we have formulated the Poisson problem in a weak form. So the weak formulation, weak Poisson, eventually boils down to finding among all possible electrostatic potentials V, the V bar that minimizes the following functional U, E, let me call it star, because UE is the electrostatic energy, which is the work due to the external forces. UE star is minus that, which is the work due to the internal forces. So UE star is the internal forces. This is a functional of capital V. Among all these, we need to find the one which has to minimize 1/2 epsilon naught volume integral in the region capital omega where the eventual charge distribution is defined, the gradient of V, quantity square, volume element dr quantity cube, minus the integral on capital omega of rho V dr cube. This is the functional we want to minimize. In the case of conductors in macroscopic electrostatic equilibrium, well, we know that this rho has to be equal to 0 at each point inside capital omega. Therefore, the functional becomes a simpler functional, UE star of capital V equal simply the first term, which is 1/2 epsilon naught volume integral on the region capital omega of the gradient of V quantity square dr cube. Now, suppose we want to use this functional to find the capacitance associated with a capacitor, with a system of two conductors. Well, in that case, we can equalize this. We found in the previous video the electrostatic energy of a system of capacitors, of a system of conductors, in particular of a capacitor. Now, note that was the electrostatic energy with the positive sign, but in this case, the sign doesn't matter because I'm already getting rid of this, so the signs come up the same. You can think about this, they come up exactly the same. So this, we can equalize it to 1/2 the energy we found in that video, C, the capacitance of our system. We wrote it back then as delta V square. Now, for simplicity, let's call all the delta V's as V's, but these delta V's are intended to be as such. For generality now, let's keep it still for a little while. Let's still call it delta V square, not to get confused. Sometimes people just call it V square, okay? So this is what we want to do, okay? So we want to use somehow this expression to find C. That's the aim of this video. Let me give you some context of where I'm trying to go here. Okay, so where I'm trying to go is that instead of course, I could solve all these problems using the strong Poisson problem, which is a partial differential equation with boundary conditions, totally general. However, if I integrate and I rewrite that Poisson problem as the integral of the gradient of V quantity square, any error in V will be second order because this gradient gets squared, okay? So somehow this weak problem has this advantage over the strong problem. And so we can use it somehow. The idea is to guess. Suppose we don't know the solution for V. Somebody gives us this equation. We don't know what is V. We want to guess it. Of course, if we are lucky and we guess right away the special V bar which minimizes this problem, then we found the exact solution of the problem. But suppose that we guess some V We plug it inside this expression, and from that we try to find this capacitance, which is a guessed capacitance, okay? This guessing procedure, again, is basically the foundation of finite element method, which is based on the Galerkin method, if you want, and Sobolev spaces, if you will see this in some other course. This concept is exactly the concept of Sobolev space. So this is quite interesting because FEM, so finite element method, COMSOL simulation, and all these beautiful things, they all come from this kind of approach. So I'm trying to give you a sense of how this method actually is used in real life. And as I already said in another video, in my lab we use this constantly. So when we have a complicated structure with capacitors, with bizarre shapes, then it's very hard to find the capacitance of this object. And so we try to guess a potential, which eventually gives a reasonable solution. And that's what we do, and actually works really well, as I will show you in this video. Let's start with a simple example for which we know already the solution. Of course, we know the solution, so why to bother to do it with the Feynman method? It's just because it's pedagogically interesting, because we know the solution, so we can make a sort of sanity check to see if it makes sense or not. So let us consider, as an example, an infinite cylindrical capacitor, which has, again, 2 walls. So there will be the outer wall, sketch it here, in this fashion, and this is the inner wall. This is indefinitely long. This is some length, capital L here. Okay. Okay. And this is indefinitely long, so it continues here to infinite and down here to infinite as well. Let us consider, as always, a cylindrical coordinate system, where this will be the everything continuous. Also, this one, of course, is indefinitely long, to be precise. Similarly, down here, the length of this object, let's call it capital L, very long. We use a cylindrical coordinate system. This is the z-axis of such a coordinate system. This is the origin. This is the coordinate r. Let us define the inner radius of this inner cylinder, small a, and the outer radius of the outer wall, b, small b. So A is the inner radius, B is the outer radius, R is a generic point. For example, if we're going to consider some point within the 2 cylinders, which will be at a distance r. There is vacuum, of course, between the 2 cylinders. One is positively charged and the other one is negatively charged, is a capacitor. Okay, so in particular, we want that the electrostatic potential V1 is equal to V at small a, whereas V2, which is V at B, we set it to 0. Okay. We can always set 0 wherever we want for the electrostatic potential. In this case, we set V2, which is V at B, equal to 0. All right. So now that we know all that, we want, so the idea is to use this weak formulation here. Let me circle it so that we know what we are attempting to use here. Guess. We want to guess a V, which, if we are lucky, could coincide with V bar. If, of course, we are lucky and we guess a V, which is exactly V bar, the one that minimizes this functional, then we get the exact solution for the capacitance. But if we guess any other V, let's call it V tilde, okay? So then if we guess any other V, which is not the one that minimizes it, this is not the real solution to the problem. Therefore, we are going to get, as a guessed capacitance C tilde, something which will be necessarily larger than the actual capacitance C associated with the actual minimization V bar, the one which minimizes this problem. So only the one which minimizes the problem, not only is the solution to the problem, which we could find by means of Gauss's theorem here if you want, and symmetry arguments, or by direct integration, that one will give the exact C, which, since this is a least action principle, means that any other V tilde will give some capacitance which is going to be a little bit larger. Least action principle is consistent with that. The beautiful feature, as already said before, is that any error in V is second order in V, actually. Because it comes in here, there is this square. So it's second order in V, which is the beauty of this problem. So this mitigates any possible error we would do by guessing a potential which is not the right electrostatic potential. This is the beauty of this problem here. Now, as it turns out, we know from Fis 242 the capacitance C associated with the cylinder. And in particular, if we calculate the capacitance per unit length, because this is an infinitely long cylinder, so let's compute the capacitance per unit length, and then we could set this length for simplicity to be, let's say, 1 meter, so we don't have to think about it anymore. If you look back at 242, it was one of the problems in 242, one of the home assignments. This is equal to 2 pi, and you can also reprove it very quickly, epsilon naught, divided by the natural logarithm of small b divided by small a. This is the capacitance of an indefinitely long cylindrical capacitor. All right. Now, let's proceed with the interesting part, with the fun part of this problem, okay, which is going to be in the second part of the board here. So the fun part is we want to make a guess. Now, of course, we know that the electrostatic field amplitude E associated with something which is cylindrical, how does it go? Well, an infinite straight line is lambda over 2 pi epsilon naught r in the denominator, so clearly this has to go as 1 over r, okay? Which means V goes as the natural logarithm of r. We've seen this also in a previous video in this course, okay? So this is the exact solution. Suppose that we don't know that. Suppose we don't know it. So I just say we don't know this solution here, and we don't want to bother to find it. Again, in this case, it's simple. But for example, if I give you something with completely strange shapes, well, then, I mean, this could be quite complicated to find. It could take like a day of calculation to find this E and this V. So instead, I hypothesized that V goes linearly with R. So this is my hypothesis. My guess, I guess, a V which goes linear with R. Is it correct? Clearly not. It should be logarithm of R, natural logarithm of R. This means even that E is going to be constant because E is minus the gradient of V. So this means that E would go as a constant. Clearly, obviously, absolutely not the correct answer. I'm guessing something, which doesn't have to be the right answer. It's actually completely wrong. However, the beautiful thing is that it's still consistent. It is still consistent with the symmetries. So you need to be careful. At the very least, you need to be consistent somehow with the symmetries. It is consistent with V proportional to R is consistent with the symmetries. Now, we also need to fulfill the boundary conditions so that V1 at A is V at A is V1 and V at B is 0. So one possible guess, which is easy to find, is V, function of R, is going to be V1, which is this quantity here, times 1 minus small r minus small a divided by b minus a. And now I let you do the calculation. Of course, if you substitute a, I get V1. If I substitute b, I get 0. So I get exactly this boundary condition. So this one is my guess. This is my guess for the electrostatic potential, which is not, as we know, the right solution. I just guess 1. The simplest came to my mind. A linear which is consistent with symmetries and gives these proper boundary conditions here. What is the slope of this potential? The slope associated with this potential is quite simple to calculate, is simply minus, because of this minus here, V1 divided by B minus A. This is the slope. But the slope is nothing but, if you want, this is basically the gradient of B, if you want. It's basically the gradient of V. The minus sign doesn't even matter because the gradient of v gets even squared. And so now what we want to do, we have our gradient, which is our slope. We want to plug it inside this functional. So gradient of v square is going to be v1 squared over b minus a squared. We plug it in here and we get the following equation, equating to what we want to guess. So here we are trying to find the capacitance, which we call C tilde, is our guessed capacitance. So it's not the real one. It's going to be, in fact, it should be larger than the actual C calculated by this means. And again, it's all for a unit of 1 meter, okay? So I'm making it simple for L equal 1 meter. So I can forget about this normalization by L, by capital L. So 1/2 C, and then I need to have delta V square, which obviously is V1 minus V2. V2 is 0, so it's simply V1, this V1 quantity square. This has to be equal to 1/2 epsilon naught. So this functional here. 1/2 epsilon naught. Now the volume integral. So we need to consider a small volume. So the volume will be the volume of a little cylinder which goes from R to R plus dr. Okay? For a unit length of 1 meter here, clearly this becomes simply the line integral from A to B in dr, which I'll put at the end. And so now we're doing the square of this slope, which becomes a positive V1 square minus V1 square minus V1 quantity square is V1 square divided by B minus A, the whole quantity square. Okay, so I do the gradient, which is the slope square. Now the volume again is for 1 meter. I already integrated the angle, which gives me a 2 pi. So the last part of the integral, so this has to be 2 pi r dr. Okay, so this is our volume integral. It becomes as simple as that. Okay, so 2 pi r dr, and then for L equal 1 meter. So that's exactly what we end up getting here. If you perform this calculation, I'll let you do it. It's rather simple. You will find that the capacitance that I guess, C tilde, so it's a simple calculation, right? You just get 1/2 r squared, so it becomes b squared minus a squared, and so very quickly you can find the solution to this problem here, okay? So it becomes a rather simple calculation to integrate this in R, so I will let you do that. The final result, of course, V1 squared, for example, V1 squared cancel out, and then some pi remains, and then you need to see what else cancels out. But basically, the 1/2 also in a way or another will cancel out, and so you end up having simply the trivial integral pi epsilon naught, which multiplies b plus a divided by b minus a. Okay, so that's the result of this simple integral here. All right. Pi epsilon naught b plus a divided by b minus a. So let's circle it. This is our key result here. Now, we want to compare this result with this result, again, assuming that this one is just 1 meter. So we get rid of it. Okay? This C tilde, which is the one I guessed, is function of pi epsilon naught. Also here there is a pi epsilon naught, b and a, and also here there is a b and a. Of course, here is in the logarithm, and here is linear. So if you look up, this actually is done by Feynman, this table which I'm about to sketch down here. So here I will just report it for you. And so we will have 3 entries. So in one, we have the ratio b divided by a, this b over a, which tells us is the aspect ratio. So how, what are the relative dimensions of the inner conductor versus the radius of the outer conductor. So in this table, let's have in one entry b divided by a. Then in the next entry, we have the actual c, this one, and let's renormalize it over 2 pi epsilon naught. So it's this for L equal 1 divided by 2 pi, so it's just 1 over logarithm, natural logarithm of b over a. And in the last entry, finally down here, we are going to have our guessed C tilde divided by 2 pi epsilon naught. We do the same normalization, of course, and we want to compare. What do we expect? Again, any value that we put in this column here should be a little bit at least larger than C, because clearly this potential is not the right solution, so it should not minimize this. Of course, if I guess this as the potential, something which goes as logarithm of R, then I will get the right result. But since we didn't, we know that this C tilde should be larger. If not, something was wrong, obviously. Something went wrong. Okay, but it didn't. All right, so then let's look at these numbers. So Feynman chooses suitably to for 10 and 100. For 10 and 100. And then it also gives another set of entries for smaller values of 1.5 and 1.1. So here we have relatively large ratio, larger and larger, and here we have small ratio. Okay. So in this case, in the case of 2, the actual calculation will give us 1.442, whereas the C tilde gives a 1.500. 1.500 is a little bit larger than 1.4. So check on that. Clearly, we get something which is a little bit larger as expected from the least action principle. But look at that. Already in this range, we are very close. So with this wild guess of a very strange random potential, which is linear enough, completely wrong, yet since the error is second order in V, when I plug it into this weak formulation, C tilde is a little bit larger, yes, least action principle, but look at it, 1.5, 1.442, almost the same. And this 2 is already relatively large B over A, okay? Of course, what do you expect? Will it get better or worse when you go down? Pause for a second and think about it. If you thought about it, you should realize that when this B over A is on the order of 100, we are talking about basically like a tiny, tiny wire with a huge outside core wall. And so in that case, clearly we have a huge variation of distances. The distance is huge between these walls. And so the real electrostatic field potential change wildly in this range. They change a lot. So the error that you expect, since we're guessing a completely wrong potential, should be bigger and bigger and bigger. Bigger error if you go from 2 to 100, okay? So the smaller error should be for 2. And in fact, if we look at the numbers, we get for 4, 0.721 is the actual result, whereas the guess is 0.833. Still not so bad. Then for 10, we get 0.434. Whereas in the guessed one, we get 0.612. So here already starts to get much worse. And finally, for 100, the worst case scenario here, 0.267. And the guessed one is 0.510. So here there is an error of a factor of 2, because really we are considering a huge aspect ratio. If we keep the aspect ratio in this sub-range, which is like even less than 2, so basically the 2 A and B are almost the same, so then we get, for 1.5, we get 2.4662, and for the C tilde we get 2.5, so very close, and even closer, within almost nothing, in the 1.1 we get 10.4921, versus 10.5. Look at this. This is almost the same. So this last entry, it's really unbelievable. We get almost the same result when the aspect ratio is so small. Okay? When I've seen this as a student for the first time, I was simply amazed. I think this is one of the best examples of physics all over, I would say. It's just amazing that, considering a structure, in this case, of course, it's simple, so we know the result. We choose then a completely wrong potential, as long as it's consistent with the symmetries and the boundary conditions which I choose here. I use the weak formulation to find the capacitance, and look at these numbers. I almost get it right. Just up to second order here is the error in V. Imagine now that instead of having this, I have some strange thing, like a capacitor, which looks like, so this is the inner conductor, and it's something like, for example, a chip that we do in the lab, right? So we have an inner. So this one is, the board is silicon, this one is aluminum in blue, and then I have a structure which is around like that, and this is conductor aluminum as well. So this is our first wall, and this is our second wall with the dielectric, let's say vacuum silicon is like a dielectric as well. We will study this later on. Imagine to find the capacitance of this by the strong formulation of the Poisson problem. Well, you need to find the electric field here between these walls exactly. And so this one requires a pretty complicated solution of a pretty complicated partial differential equation. Instead, you can try to guess, now we're not going to go into the details of that, to guess a potential for this and see what happens. Actually, this is quite an extreme case. But for example, you can, and I will let you think about this in Piazza. This is not easy, okay? So I don't expect a solution. But you can think, for example, if I have, can I use this method to compute the fringing effect? If I give you a parallel plate capacitor, the fringing effect, so of course, if it was ideal because it's long, the field is just straight like this, but here I will have some fringing effect. Can I use the least action principle to take into account for this fringing effect? As it turns out, yes, and I can find a very good approximation. So this is a beautiful, beautiful method. In the next video, I'm going to go even more into details to guess another and more complicated potential, which allows us to make a minimization so that we can further refine our knowledge of C tilde. That's it.